right, so the next thing we're going to use our probability for is to calculate something called the expected value of an event. Now, expected value, it affects your life. You probably are not aware that it does, but things like insurance costs are based on expected value. Anything that happens, anything where there's chances of successes or failures, or there's different options and happens repeatedly, is based on expected value. So the expected value is the average result over the long term. If you remember our law of large numbers said to us that probability only has meaning when we're talking about a large number of experiments. Okay, in the short term, probability doesn't really have much meaning. That's why when you turn on the news or you look on your app and it says that there's a 30% chance of rain, it's saying over the course of all days that look like this and have these similar conditions, 30% of the time it's going to rain. In and of itself, that's the only way probability has meaning. So the way that we calculate expected value is we find the product. What does product mean? Product, what mathematical operation does product mean? Multiplication. Yes, the outcome is going to be gotten from multiplication. So we're going to calculate this by finding the product of each outcome's probability and its net result. And then we're going to add all those together. The way the book writes this is the expected value looks like this. It's the probability of the first thing happening times the net amount of that first thing, plus the probability of the second thing happening times the net amount of the second thing. And now I'm not going to write this all day. I don't know how many outcomes we have. So then we have the probability of the last, which our book uses the letter N. The probability of the nth thing happening times the amount, the net amount of that. Now, if you don't like formulas, that's fine. Okay, we're going to go through a bunch of examples. Basically everything in this section now, you know everything that you need to know. We're going to apply it so that hopefully you get adept at applying this little formula. So my first example looks like this. JetBlue is considering adding a new route from Boston to Minneapolis. Okay, but companies don't do things to lose money, so they do market research. Anytime you see a McDonald's or a Publix pop up somewhere, they've done a lot of research about traffic patterns. It's all based on expected value and probability and stuff like that. It underlies a lot of business practices. So after they've done their market research, JetBlue estimates that if it adds the route, there's a 60% chance it's going to make a profit of $800,000. There's a 10% chance that it'll break even, and there's a 30% chance that they'll lose $1 million. Okay, everything's a risk. So what's the expected value to them as a company if they add this route? Okay, so here we go. E stands for expected value. I'm just going to abbreviate because I'm lazy. In the paragraph, I told you there was 3 things that can happen. They could make money, they could break even, they could lose money. Which one you want to deal with first? Make money. Yes, we always want to make money. I'm glad you're the optimist. Okay, so what's the probability that they make money according to the problem? 60%, so 0.6. We'll use the decimal, 0.60. And then what is the net amount that they are going to gain if they do make the money? 800,000. Perfect. Okay. So there's my first outcome. That's the make money outcome. You don't have to write this down when you do the problem. I'm just doing this for your notes on this first problem. This is the outcome that they make money. So then, what second outcome do you want to consider? Sure, lose money. Well, what's the probability that they lose money here? 30%, so 0.3. And then how much do they lose? $1 million. So I'm going to make that negative, okay, because we're losing, and it's negative $1 million. So you're either all in or you're all out, I guess. Notice what I'm doing each time. It's the probability times the net amount. Probability times the net amount. Then the last thing is they could break even. And break even is a 10% chance, so 0.10. And if you break even, what is your net result? 0. Yep. So just wanted to make sure to cover that in case you weren't familiar with that. At that point, once you've gone through every outcome and you've done its probability times the net result, it just becomes a calculator problem. So it's not too big of a deal from there. So now I've got 0.6 times 800,000. That is going to be 480,000. And then I've got 0.3 times negative a million. That's going to be negative 300,000. And then 0.1 times 0, anything times 0 is 0, so I don't have anything on that last term. So then I have 480,000 plus negative 300,000. And that is going to be positive 180,000. So over the course of the long term, over the course of many times running that route, they expect to gain value. Sometimes they're going to lose, but more often they're going to gain. And so the average over the long term is going to be that they gain 180,000 every time. So if you were a decision maker for JetBlue, you would then say, yes, that's something we want to do because we expect in the long term to consistently make money. If this was a negative and you were the decision maker for JetBlue, you would say, no, we don't want to get into something where we expect to, over the long term, lose money consistently. And that's the determination that expected value helps you make. So I have a very similar first problem for you to do, just so that you can run through calculating your probabilities and your net amount. So exercise 1 is you are considering purchasing a stock. All right, so yours is very similar, just changed the context and the numbers, create a nice simplified example so you could run through this. So according to your investment app that you're using, you have a 70% chance of making money, a 10% chance of breaking even, a 20% chance of losing money. So here we go. You can do these three products in any order. So if you picked yours in a different order than me, that's totally fine. So I'm going to be the optimist, and hopefully we're going to make money. So there's a 70% chance that I make $15,000 according to the problem. Great. And then plus there is a 10% chance that I break even. So 0.10 times 0. And then there's 20% chance, because there's risk in everything, there's 20% chance that I lose money. So that's negative $8,500. Before we get to the calculator portion of this, is there a question about this up to this point? Are we doing all right? Again, it's all based on probability. That's why I just wanted to make sure that you took that first section seriously. So now I'm going into my calculator here. And so 0.7 times 15,000, I think you should get 10,500 for that. And then 0.2 times negative 8,500, what's that? Negative what? 1,700? Sounds great to me. And so when I add 10,500 and negative 1,700, it looks like that's going to come out to 8,800. And it's in the positive. So you have that kind of money laying around, good for you. Then that seems like it'd be a good investment, because again, over the long term of investments that have those same sort of conditions, you are gaining rather than losing. Give exercise 2 a try. It's a different situation. Now you're not using it as in relation to money. You're an event organizer and you want to know how many people you should plan for attending an event. So go ahead and give that one a try, please. All right, so the expected value is going to be the probability times the net result for each outcome. How many outcomes do I have in this particular problem? 2. What are those outcomes? It's either going to rain or it's not going to rain. Those are the whole thing that we're focusing on. Okay, so here we go. We're told that there's a 30% chance of rain. So I'm going to start with that. Again, if you did not rain first, it doesn't matter. How many people are coming? What's the net result if it rains here? 12,000. Great. So I'm going to put 12,000 right here. Plus, well, if there's a 30% chance it rains, what's the percent chance that it doesn't rain? 70. Again, just like with odds that we talked about in the last section, all of your probabilities, when you add up the probabilities, they should add to 1 because you're considering every possible outcome. Okay, so when you add up the probabilities of every possible thing that can happen, that turns out to be 1. And so then the net result there is 20,000. All right, before we get to the calculator portion, anybody got a question? Anything go wrong for you here? All right, well then 0.3 times 12,000, is that 3,600? All right, the mental arithmetic's working okay this morning. Plus 0.7 times 20,000, is that 14,000? All right. And so that means if we are planning for this, then planning for about 17,600 people would be reasonable, because you're going to, many times you're going to get the full 20, but many other times you're going to get 12. And so your net average over the long term is going to be 17,600. All right, I've got another example and then a few more problems for you. I'm just trying to show you every situation you're going to encounter when you go through your homework. So this next one, Josh is going to a charity event. and he purchases a raffle ticket that offers a $50 prize. So this first example of a raffle is just the simplest type of raffle you can have. There's only one prize. We're not complicating it with multiple prizes. We'll talk about that in a minute. So like the lottery, if you play the Florida lottery and you pick your numbers and everything like that, that is a much more complicated expected value because you could win on different, like 4 numbers out of the 6 and 5. But in essence, it's this same thing. Okay, so Josh buys 1 ticket for $2. 100 tickets are sold. Let's determine Josh's expected value. Okay. Well, what are the possible things that can happen for Josh here? He either wins the 50 or he doesn't win the 50, right? So again, let's be optimists that Josh wins the $50. If he buys 1 ticket and there's 100 tickets sold, what's his probability that his ticket number is drawn? 1 out of 100. Perfect. Great job. That's the probability that he wins. How much does Josh win? Now, let me pause. I'm going to call a timeout. Remember, we are talking net result. Don't forget to take into account that Josh paid $2 for the ticket. He wins 48. Yes. So when he goes home, his wallet is $48 richer. Does everyone understand why that's 48? He paid $2, so he's negative $2 to start out with. Somebody hands him a $50 bill, so that means he's gained $48 from when he started. Okay, so we have to take into account. So make yourself a little note. This is the first time this has happened, that you have to take into account that it's the net result. Kind of like on your paycheck, you earn all that money and then the government grabs theirs and your net result looks much different than what you would hope for. Okay, so then plus, well, if there's only these 2 things that can happen, there's not another prize. If there was a $10 prize, we would consider that next. We would consider each of the different amounts you could win separately, but there's not here. So the only other thing he's going to lose. What's his probability that he loses in this lottery? Yep, the other 99 tickets are no good for him. And what is his net result when he loses? -2. He's out that $2. He's donated that to charity. All right, I'm going to use decimals just to make this go a little quicker. 48, when you divide that by 100, is going to be 0.48. And then 99 times -2 divided by 100, I think that's going to be -1.98, but I'm going to verify, yes, it's -1.98. And so that gives Josh an expected value of -$1.50. So what that means is in the long run, remember, expected value, like all probability, only makes sense with a large number of trials. So if Josh does this repeatedly, most of the time he's going to lose his $2. Every once in a while, he's going to win that 50. So that means the average, if I add up all of his winnings in the long term and divide by how many times he played, the average is going to be he's losing $1.50 every time he plays. So a negative expected value means he is losing. Now, I don't know if you are fond of these things, if you like gambling, games of chance, if you're a slot machine person or you like to play whatever. I'm not a gambler because I know the mathematics behind it. Every game that you could possibly play. So when you go on the cruise ship, if you go into the casino, okay, every game you can possibly play has a negative expected value from your point of view. Every one of them. So that means sometimes you're gonna win and it's gonna be exciting, but then most of the time you're giving your money away. So just know that going into the endeavor, that there's no game that has a good expected value. So there's another question right here. I asked as a second question, what's the fair price of this game? So the fair price, what that means, again, I mentioned this last time. Fair mathematically, we're not talking about the morals of it. What we're talking about with the fair price is so that the expectation is 0. what would we charge for a ticket so that the net result in the long term is 0, so a break even. So the way you calculate that, I'm going to abbreviate, the fair price is equal to the expected value plus the cost to play. Okay, it's just a nice, simple little last calculation. So when we're asked for the fair price of this, what we'll do is we'll take that expectation, that negative $1.50. We're going to add to it the cost to play. Josh paid $2 to play this game. And so the fair price would be 50 cents. So the fair price, meaning that Josh's expected value would be 0, is 50 cents. All right, we're going to turn the page in just a minute, unless there's a question. Anything you got for me? All right, lovely. Then exercise 3 is a very similar question. I just changed the numbers so that you get to work through it. So do the same 2 things. Figure out the expected value of this basic lottery, and then what is the fair price. All right, just like the last problem, there's 2 things that can happen. This is the simplest type of lottery that there is. You either win the $600 or you don't. So again, $2 ticket, this time 1,000 tickets are sold. So what's the probability? Let's be optimists. What's the probability that I win in this raffle? Okay, 1 out of 1,000. Fantastic. And then what is my net result? $598. Fantastic. You paid the $2, then you won the $600. So you are ahead of the game by $598. Fantastic. Now we're losing. What's the probability that I lose? Yeah, it's almost a certainty, probability speaking. It's 999 times out of 1,000, you are going to lose at this. And then what is your net result when you lose? -2. Beautiful. The rest of this is just calculator work. 598 divided by 1,000 is 0.598 plus a negative. When I do -2 times 999 divided by 1,000, what does that end up being? 1.998. Did I hear you right? Okay. 1.998. Lovely. And so I'll add those together and it turns out to be negative dollar, is that $1.40? Again, it's weighted against you, as all lotteries are. So as you play this in the long term, you could also think about this from the perspective, we could flip it around from the perspective of the person that's planning the lottery, which probably makes a little more sense. The person planning the lottery, they're not losing, they're gaining. They're gaining $1.40 for every person that buys a ticket. So that's what they know. All right, so that's the expected value if you buy a ticket, and then the fair price on this ticket is the expectation, which is the negative $1.40, plus the cost to play, which is $2. And so the fair price of a ticket here, so that the expectation works out to be 0, would be 60 cents. We doing all right? All right, just a couple more examples. Again, I'm just taking you through the different things that you'll possibly see when you're going through these problems. So exercise 4, I complicate the lottery a little bit. We have multiple prizes. So in this one, there's 10,000 tickets, $5 each. 4 prizes are going to be awarded. There's a $5,000, a $2,500. There's $2,000 prizes. I ask you to make an assumption here. It's not quite 100% accurate, but we haven't talked about what's called conditional probability. We'll talk about that when we come back after the break. So we're just going to assume the probability that any individual ticket would win would be 1 out of 10,000. So if you purchase 1 ticket, what's your expected value? And then we'll do the fair price. So here's what I would like you to do. We're just going to do this together because it's a little more complicated. So the expected value. So the first thing I want you to do is I want you to write down what 2 things are you going to multiply together if you were to win the $5,000. Okay, what's the probability you win the 5,000 times the net result when you win the 5,000? I'll give you 15 seconds to write down what you think that product is going to be. All right, what's the probability that you win the 5,000? Perfect. You have 1 chance. There's 1 $5,000 prize out of the 10,000 tickets that are sold. And what's your net result if you win the 5,000? Great job. $4,995. Well done. Okay. I'm going to give you another 10 to 12 seconds. Do the same thing for the $2,500 prize. What's the probability times the net result for the $2,500 prize? What's the probability that you win the $2,500 prize? 1 out of 10,000. Yep, I said for any individual ticket, we're keeping this simple, and we're just saying any individual ticket has a 1 out of 10,000 chance of winning. And then what's your net result if you win this prize? Okay, great. The reason I'm just taking this slow, part of it is this next one. Now we don't have 1 $1,000 prize, we have 2 $1,000 prizes. So that's going to change the probability just a little bit. Okay, so make your best hypothesis on what that product's going to look like. What's the probability, do you think, here? There's 2 prizes, so it's 2 out of the 10,000. Does that make sense? Okay, there's two of these prizes, so 2 of the tickets are going to win. So there's 2 chances out of the 10,000. Then the net result is $995. And then last, you might have already done this, but 10 seconds, write down the other outcome. What's the probability? There's 4 prizes, there's 4 winners, so that affects the probability that you lose. Okay, what's the probability do you think that you lose here? Perfect, 9,996. Not 900, not 9,999, okay, because there's 4 winners. That means the rest, the 96 are the losers there, okay? So I'm just trying to point out the common mistakes. So if you made that mistake, forgive yourself, it's okay, it's a very common thing. Just use that as an opportunity to learn. And if you lose, you're out your $5. The rest of this just becomes a calculator issue. So the first one, 4,995 divided by 10,000 is 0.4995. The next one is 0.2495. The next one, I've got 995 times 2 divided by 10,000. That is 0.199. And then finally, I've got the last one. I've got -5 times 9,996, and then divide that by 10,000, and I get -4.998. And now I'm just adding those numbers together. Maybe you're doing the same thing. And it turns out to be the expected value is -$4.05. So whoever is running that lottery is looking to make money, because it's a pretty well weighted, something like a slot machine. Like if you've ever tried one of those or enjoy that, something like a slot machine is, a lot of those are weighted like by the penny. So every time you play, your expected value is like -2 or 3 cents. But the thing about slot machines is you just keep feeding it, and lots of people are doing it. And so it's the law of large numbers in action. Not any one particular one sinks you. It's just the culmination. All right, so the fair price is the expectation plus the cost to play, which is $5. And so then that means the fair price, what should be charged for this, if everybody's going to break even, is 95 cents, which is kind of an awkward price for a lottery ticket. Lots of nickels given back to people. Okay, so just 2 more problems. We're doing great on time. So if you have any questions, please don't leave here with questions because you felt like we were rushing through or anything. I want to help you any way I can. So insurance, the price you pay for insurance is fully based on probability. So like this particular problem says that a 20-year-old woman, we don't know any other things like habits or anything like that. We're just keeping this generic. Will live 1 year. The probability that that 20-year-old woman will live 1 year is 0.994. So there's huge tables of numbers for ages and for pre-existing conditions, and if you're a smoker and things like that. There's all sorts of probability table called actuarial tables on all of this stuff. As far as like if you're for driving, accident rates and things like that at different ages. That's why as you get older, your auto insurance tends to go down, is because you get less crazy as a driver the older you get. And if you want your auto insurance to go down even more, have a baby, because people with babies drive even less crazy than everybody else usually. So all of it's probability. So anyway, all that to say is this is, again, a super simplified example. We want to know we're doing this from the insurance company's perspective. We want to know for every 20-year-old woman that the insurance company can sign up for a 1-year life insurance policy, what is their expected value? I need to tell you one thing, though, that I left out of the problem. I don't remember the amount, so I'm just going to make up an amount here. Let's say that it's a $100,000 policy. Okay, so I don't even remember. Let's say it's 10,000. That doesn't sound right. Okay, so I didn't say it in here, but if the 20-year-old woman buys a 1-year life insurance policy, buys a 1-year $10,000. So that means if she dies, that her heirs get $10,000. What's the insurance company's expected value? So there's two possible outcomes that can happen for this woman, according to the life insurance company. She either makes it through the year, which is what we would hope for, or she doesn't make it through the year, and then the insurance company has to pay out. So give it a try, give it your best effort. I'll give you a minute or two to try to set this one up. So insurance is all about law of large numbers. The reason you buy insurance is, in case that, you have health insurance in case that catastrophic thing happens to you, but hopefully, you live in good health. So you don't really notice that you have the insurance. But for the insurance companies, since they're paying out, they need to sign up lots of people in order to get this. And of course, insurance companies, it's complicated by government regulations and greed of companies and things like that. So nothing's altruistic. But anyway, so if you're the insurance company, okay, what's the probability? Let's be optimists. We want this person to live through the year. What's the probability that this woman lives through the year? Okay, 0.994, almost a certainty. If you're the insurance company, what is your net result if this woman lives through the end of the year? You get $100, right? You get her premium and you get to do whatever it is that you do with that $100. Okay. Plus, what's the probability that this woman doesn't make it? Okay, it's 0.006. Remember, for our expected value, the probability should add up to 1 if we've considered every possible outcome. So 0.006. Okay, again, if you are the insurance company, what is your net result? Negative 9,900. Because at the beginning of the year, when she purchased this policy, she paid in $100. And then, so you got that, but now you're paying out the $10,000. So the net result is you're paying out the $9,900. Everybody understand why that's a negative 9,900? All right, once you understand that, the rest of this is gravy. And so what we've got here is 0.994 times 100, and that gives you 99.4. And then plus, and then negative 9,900 times 0.006, and that is negative 59.4. Okay, I think I picked the right number. That's good. So 99.4 plus negative 59 is a positive $40. So that means for every 20-year-old woman in that same category that they sign up, it's a net result of $40, okay, to the insurance company and the stockholders and all of how that works. Okay, so an insurance company would not want the expectation to be negative. Okay, that means they're paying out. And they would have to sign up lots and lots and lots, because you definitely want to be able to cover the cost for the unlikely event that somebody does pass away in this category. So things like when you get to the point in your life, if you're going to buy life insurance, that's another thing, that the older you get, more expensive life insurance gets, because the older you get every year, that actuarial table, this number here comes down just a little bit, until you're in your 70s, and it starts coming down a lot. Okay, so the probability you're going to die eventually goes up. All right, one more thing. We're almost done. Test taking strategy. Okay, you are taking a multiple choice exam in which there are 5 possible answers. So you got 5 things you could bubble in for each question. You're going to get 2 points for each correct answer. You're going to lose a half a point for each wrong answer. There's no change for a problem left blank. So here's the A problem. Here's the A problem. If you do not know the answer given these constraints, is it to your advantage to guess? So let's set this up. We're going to see it's an expected value problem. Okay, so let's try this. So my expected value. So if I guess on this test, what are the possible things that can happen when I guess? You get it right or you get it wrong, right? There's only two possible outcomes. So let's be optimists. I always like when I guess to think that I've guessed right for some reason. Okay, so if I have 5 possible things I could bubble in and I'm guessing, what's the probability I get it right? Okay, 1 out of 5. By the way, on a multiple choice test, the best, because most teachers are not good test makers, the best possible option is B. Okay, so if you have to guess B, because the reason why, I learned this in my statistics for teachers class, is because most teachers make their best distractor and put that as A, and then they run out of ideas, so they put the right answer as B, and then they put in some other things. So statistically, the best guess you can make, not that I want you to guess, I want you to know what you're doing, but B. All right, so anyway, so you 1 out of 5 chance that you get the right answer, and then what is the net result if you guess right? 2 points, right? And then what's the probability that I guess wrong on this? Okay, 4 out of 5. And then the net result is that I lose a half. So I'm going to use a decimal there, negative 0.5. So put this all into my calculator. 1/5 times 2 is 2 times 1 is 2 divided by 5. That's 0.4. And then a 0.5 times 4 divided by 5 on the other one is negative 0.4. So that means if you went along happily guessing, if you Christmas treed that test under those conditions, you're going to end up with a 0, because sometimes you're going to get it right and get those 2 points, but most of the time you're going to get it wrong and you're losing that half point. So guessing has no advantage for you. It has no disadvantage, okay? No net result. So then the B problem says this, because this is always what you should do if you do have to guess. You should look at the distractors and see, can you eliminate any of them? So let's pretend that you can eliminate one of the wrong choices. Okay? You know one of them is so very wrong. Okay, and so you're gonna admit that. Now is it to your advantage to guess? So go ahead and do the calculations real quick. Find the expected value. I'm going to start while you're working. That way we are all done and settled on time. Okay, just for time's sake, I'm sorry, I didn't give you adequate time on that, but I always like to let you out on time. So the only thing that changes here, since I could get rid of one of the wrong answers, is my probability of getting the problem right. So now instead of 5 possible options, there's 4. So my probability of getting the problem right is 1 out of 4, and I get 2 points. My probability I get the problem wrong now is 3 out of 4, and I lose my half a point. And when I do all the calculations, my expectation is positive. So that means, yes, it would be to my advantage to guess, because I'm going to end up with a net gain at the end of it.